Sidney Perkowitz, welcome back to the program.
Oh, it's such a pleasure to be here, Russell. Thank you.
Sidney Perkowitz is the Professor Emeritus of Physics at Emory University. Sidney has authored many research papers and books, including Empire of Light, Universal Foam, Digital People, Hollywood Science, and has just recently re-released an updated version of Universal Foam for Kindle called Universal Foam 2.0, From Cappuccino to the Cosmos. Sidney, why have you decided to update this book? Why have you decided to re-release a book that's 15 years old?
Yes, it is interesting how far back it goes. And when it first came out, it was before there were barely any e-books, and this never appeared as an e-book edition, although it appeared in several print editions in different languages. So it actually got printed in different editions from 2000 to 2008. So I said there were two sets of reasons. One reason is almost everything in the book has gotten more interesting and better. A lot of the science of foam has progressed, and even a lot of the use of foam in the kitchen or on the battlefield or any other practical application has also changed. So there really was enough for a reader to say, you know, stuff has happened since 2000, let me look at it again. And the second thing was this was a way to dip my toe into the sea of doing e-books. Any book I write now does come out as a hardcover and an e-book when a regular publisher does it, but I wanted to explore what it felt like to do a book all on my own, and this gave me a great opportunity to do that.
Foam in the battlefield.
Yeah, so the first thought in your mind is that we're now going to fill artillery shells like Nerf balls. That's not what I mean. I mean something a little more peaceable and really a good thing on the battlefield. If, God forbid, you or one of our soldiers are injured on the battlefield and maybe there's an abdominal wound that needs to be sealed up, but they've developed this foam that can be sprayed in. It expands to fill whatever it needs to expand, and it provides both some antiseptic and also structural support so that whatever has been damaged while the soldier is being transported to the hospital is held up and nothing collapses further. And apparently this is done really, really well, and of course it's not just for battlefield use. You could use it wherever there's been an auto accident or whatever, any kind of trauma. But like a lot of things, it was pushed by developing good medical capabilities for our soldiers. There's another way it's used, too. It's not exactly battlefield, but people have developed anti-terrorism foams. So if you think that there's a ticking bomb and there's no way to stop it from exploding, one option would be to cover it with a big mound of foam that won't completely eliminate the explosion, but it'll damp down the effects enormously.
This would be better than encasing it in concrete.
Encasing it in concrete would be great, but you can't do that very quickly. If you've got only half an hour, or like in all the science fiction movies, you'd see it count down from 30 seconds to 0 seconds. That's all you got.
And you've got two choices, the green or the red wire.
Right. Fortunately, usually the hero picks the correct one.
I've never seen them pick the wrong one, actually.
You know, actually, you're right. Well, Hollywood does not like downer endings, so that would definitely be a downer.
So this is kind of like mono foam insulation.
Yes, it's the same kind of idea, except it's provided in liquid form, and it would be almost like spraying it out of a fire extinguisher cylinder. It comes out as a liquid, and it firms up very, very quickly, or maybe even remains semi-liquid. That would be good, too, and then provides a barrier that you didn't have 1 minute ago.
Is foam a liquid or a solid?
Technically, if you take the most technical definition, people almost always think of it as a mixture of liquid and gas, so that makes the liquid definition front and center. But you can make things that look like they're a mixture of a solid and gas, and that could probably be called a solid foam. Most people don't think of that, but really it is. Or some people would just give it a fancier name. They would call it a cellulose solid. But in my book, I included both the liquid type and the solid type.
This may sound like a stupid question, but what exactly is foam?
The basic definition, again, is a mixture of air and gas so that you get bubbles in close proximity to each other. I think that would be the most straightforward definition I could give you. And then you could extend that if you want to go to solid foams and say, well, suppose you make a liquid foam like that and then find a way to let it gel or set, then you have a solid foam.
Or it goes from a gas to a solid just like the spray foam insulation.
Right. So what's really happening there is you're mixing liquid and a gas as it comes out of the nozzle of your spray can. It comes out as a liquid. It sets very quickly, and there's that transition from liquid and gas to gas in a liquid as a solid foam to gas in a solid as a solid foam.
How large can a bubble be?
There's a gentleman who does physics demonstrations centered on bubbles, and he has come up with ways to make bubbles the size of a person. When he does his demos in front of kids, they go wild. So the bubble itself is huge. It's beautiful because you get these rainbows all over it. It's really very spectacular. I don't quite know the secret of how he does it, but he's found a good technique, the right mixture of soap and water or whatever. Maybe he adds some glycerin to make the bubble fairly sturdy and really huge.
Why do bubbles have rainbows in them?
It's because, well, let's first say what a bubble is. So a bubble, either one just floating in air or one in a foam, is really nothing but a very thin skin of liquid enclosing a sphere of air. And the key is that liquid film is very thin. It's thin enough so that when light hits it, some of the light bounces off the front of the film, and some of it goes through the film and bounces off the back, comes back and interferes with the first ray of light. You get interference, so whenever you get interference between two rays of light, you get colors, because the interference depends on wavelength, so it picks out some colors. So it's the same effect you see if you ever saw an oil slick in the gutter. That will show rainbows, too, for the same reason. Light bouncing through a thin film of liquid and then coming back out and interfering with itself.
Are all bubbles round, or can they be other shapes?
A bubble is just left completely alone in principle. It wants to be utterly round, a perfect sphere, because that takes the least energy for it to maintain itself. But you almost never see bubbles in that pure state. Any bubble you make on Earth will have gravity pulling it down, so that will distort it a little bit. And when you get bubbles cheek by jowl in a foam right next to each other, they're way different from spherical. They actually turn into polyhedrons. One of the nice images in my book shows how bubbles in a foam actually look like, if you can imagine dice that instead of having 6 faces have 8 or 10 or 12 or 20 faces. That's what the bubbles look like jammed up against each other. The only time you could probably get really, truly, purely spherical bubbles would be out in space with gravity as small as you can possibly get it.
Pressure is greater on the inside of a curved interface. If the universe were a bubble, could that explain why the universe is expanding? And could the universe be simply a bubble within an ocean of bubbles?
You know, that's really a nice question. Yeah, there are a lot of angles that would make most physicists say, including me, that at least as a metaphor, and maybe even really, the universe is either one big bubble, or if you believe in the multiverse theory, which I don't, but some do, it's a bunch of bubbles. So one big bubble, the question is, yes, we're expanding. That part of it is right, and that's what bubbles do. What are we expanding into? Well, the answer is, and this isn't very satisfying, Russell, but it's the only one you can give, we're expanding into nothing. So we're the bubble of reality expanding into reality that doesn't yet exist. That's a head-turner, right?
Yeah. As a kid, I remember trying to grasp that concept, what's on the other side of the universe, and my mind would go blank. It's quite an odd feeling.
Yeah, and I teach this subject when I taught astronomy at Emory, and part of what we cover is cosmology, the expanding universe, all those deep questions. And whenever I got to this particular question, what's outside the boundary of the universe, everyone's head would start spinning around rapidly, or their eyes would just go blank. It's a tough one. Mine, too. They weren't the only ones. Me, too.
The other one that always got me, too, was that all there is the universe. That one I couldn't quite understand either.
You know, that's semantics, and that gets you only so far. So you can say, by definition, the universe is all there is, and that's the bedrock definition. But that doesn't really leave you with much deeper knowledge, I think. So I'm with you on that. It's a word, and we're trying to explore the meaning of the word. We certainly don't know all the meanings of the word universe yet.
Do you think everything could eventually be known through science? given enough time?
But yeah, that's a great question too. I think if you limit what you mean by everything, so I believe
well,
that
you can't limit it because everything is everything, so it's unlimited.
Okay, then I would say the answer is no, because if by everything you mean not only questions like how does this work, but questions like why did it start, then I don't think science can answer that. I think science can eventually will answer any factual question we can come up with, whether it's about the physical universe or how humans interact or how animals develop, you name it, I think we will do it. I'm a big believer in that. But science is not built to answer questions like, why did it all start? Where are we going? Is there some aim to it? That's a different set of questions.
Those are philosophical questions, and they don't really necessarily have answers.
And I think that's a very smart way to look at it. I think the joy is in asking the question and trying to find maybe your personal answer or the answer you get from what you like to believe in, whether it's science or it's religion. I'm not sure there ever will be an overall answer that we can all vote on and say, yes, that's it.
Why do some carbonated beverages have froth and some not? For example, a perfectly drawn Guinness beer can actually hold a dime on top. That's how they test it. But yet a 7-Up has no froth at all.
Well, there are a lot of things going on. So one part of it is when you first open the container with the drink, let's say it's a can of soda, how much it froths depends on how much pressure there was inside. When they make Coca-Cola, and believe me, I looked into this because, Atlanta is where Coca-Cola was invented, and Coke also has put a lot of money into my university, Emory. So we treat Coke with a lot of discretion around here. We really treat it very kindly. I looked into it. Coke is very careful about the amount of pressure it puts into its drinks, and they put in a fairly high pressure, so you tend to get a head on it. Other sodas may not. So that's one difference. And then I think the other part of your question was, why are some foams stronger and some weaker? Well, the foams in a beer or an ale or a Guinness, the bubbles that form them are little cells, and the walls are made of the proteins in the stuff that goes into the drink, whether it's beer or ale or Guinness. Those proteins link pretty strongly. So you basically have a little microscopic jungle gym, if you want to think of it that way. The bars in the jungle gym are all proteins, and they're pretty strong bars. It'll last a long time, as you said, will support a weight. The jungle gym that comes out of a can of soda does not have, especially if it's diet soda, which doesn't have anything nutritional in it, those bars do not have proteins in them. They're quite weak, and you really don't have any kind of strength or durability in the foam.
In your original universal foam, you talked about an extraordinary aerogel which would be sprayed into the tail of a comet. But that would have been back in 2004. What was the result of that?
Oh, I'm so glad you brought that up because that was one of the best parts of writing the updated version. When I published the first universal foam in 2000, they were just getting ready to send off this aerogel to explore a comet. And I couldn't say anything about the results except to say that they're going to do this, and astronomers and scientists hope that aerogel will bring back really interesting information. Well, since the book was published in 2000, they did it. The experiment was a complete success. The aerogel was brought just where it ought to be, near a comet called Wild 2, WILD2. Wild is the name of the astronomer who first discovered it. It brought back chunks of chunks of the comet, and landed them in the Utah desert. They were all happily retrieved. Scientists have now been studying them for years. About 4 or 5 years ago, they started reporting some results, and they're still reporting results now. So in my updated version of the book, I was able to say actually how the experiment ended. Fantastic experiment. I interviewed the astronomer whose idea it was, and it's just a phenomenal project.
What are some other examples of things that were updated from the original?
To get out of the science and get in another area, one thing that I really found interesting is how important foam has become in cooking. I talked about this a little bit in the original edition. There were some people who did what they then called molecular gastronomy, which is kind of a mouth-filling way to say we want to try to use some scientific ideas in the kitchen and see if it doesn't make interesting dishes. And they had produced some dishes with foams and other things like liquid nitrogen. They had some really neat techniques. Just about 2 years ago, though, a gentleman named Nathan Myhrvold, he's a very interesting guy. At one point, he was the chief technology officer for Microsoft. He retired from that, bundle of money, I assume, because he bought in the early days, and he pursued a second great passion, which is cooking. And I think in 2013, I might be off by a year or so, he put out a 3, 4, or 5-volume cooking book that sold for about $400, if you can believe this. It was a lavish, lavish book with beautiful photography, and it was all about science in the kitchen. And he gave it a much nicer name than molecular gastronomy. He called it modernist cuisine. So there are all kinds of wonderful cooking techniques, and there are quite unusual things, unusual dishes, and a large part of it is dishes that involve foam. So that's another example of where, in the second version of my book, Universal Foam, I was able to bring in much more recent stuff, but this time in the kitchen, not out in space near a comet.
Yeah, you have to make the science applicable to everyday life, because the average person probably isn't thinking about foam.
In fact, I was at a writers group this week. I hang out with other writers when I can, and we were going around telling each other what we had written, and someone asked me what I'd written. I said I'd written a book about foam, and she asked, well, where does foam appear? And I said, well, have you ever had a cappuccino? And, of course, that did it. That brought the point home. If I started talking about comets and aerogel, I would have lost her immediately.
It's funny you bring up that book. I bought a nice used copy of Larousse's Gastronomique the other day. That's like the Bible of cooking. You ever heard of it?
Yeah, not only that, I've written about it because I've written other pieces about cooking, and I've done some of the history of how cooking in restaurants and so on began to be what they are today. And, of course, Larousse is just about the granddaddy of it all. Yeah,
I was happy to get it. I got it for $1.
Fantastic. There's nothing like hanging around in old bookstores if that's where you got it.
Yeah, it was a thrift shop, and, of course, I don't think they knew what they were selling.
I know. You got a real treasure there.
Well, how do you make the perfect cappuccino? I know you like to make them.
I do, and I used to do it in the traditional way. We actually had a little espresso machine here, and I even wrote about this in Universal Foam, and I'd go through it and make the espresso coffee, and then use a steam wand and foam up the milk, and it was just utterly delicious. But some mornings when I'm in a rush or just feel a little lazy, I do it a different way. This is really a simple way, and some of your listeners might like to try it. I make regular coffee. I find that there's really a little too much caffeine in espresso. I don't always use that. Regular coffee, that's fine. It's just sitting in a coffee maker. Then I take a mug, put in about ½ an inch of milk, and skim milk, and very cold. Foam's the best, by the way. I whip that up with a little hand whipper, which makes a beautiful head of foam in about 10 seconds. Add the coffee, stir carefully, put the whole thing in a microwave. In my microwave, exactly 24 seconds is the magic number, and I get a beautiful latte with a beautiful head on it. The foam couldn't be more perfect, and the whole thing is made in 2 minutes flat. So that's my recipe recommendation for the day.
There is a lot of foam in cooking now. I see on the cooking shows, they're quite often making little foams and putting them on the plates.
Yes, and there was a period there when they were making foamed soups and all kinds of unusual foamed things. People love the texture of it. The nutrition people and the food scientists call it mouthfeel. And foam just has one of the most pleasant mouthfeels around.
In Universal Foam, you talk a lot about the minimizing principle and how it relates to foam. Can you explain that for the audience?
Yes, and I found I had to give it a name because when I looked in the physics literature, it seemed it had never been laid out quite so precisely. So the idea is this. Most physical systems are most comfortable, most stable when they have the least energy available. So think of something that might be U-shaped, maybe a U-shaped bowl, and you put a ball bearing on the top of it. Well, the ball bearing doesn't want to stay there. It wants to drop. It wants to slide down or roll down to the bottom of the bowl. It minimizes its energy, is what I mean. So that's an easy example of the minimizing principle. It's a little harder to see that it applies in other circumstances, but it goes back to what I said before about a round bubble. If you take a bubble, the bubble has to maintain that skin to let it continue to be a bubble. It turns out that of all the shapes the skin could take, it takes the least molecular energy to hold it in the shape of a sphere. So the bubble's physical activities work so as to minimize the energy, therefore the least energetic shape, and it takes the form of a ball. And the minimizing principle shows up in all sorts of places. When a laser is working, it's because an electron has jumped from a lower energy level to a higher energy level, but it really does not want to stay there once it goes back to the lower energy level. So again, it tries to minimize its energy, and when it does so, it pushes out a little pulse of light. That's a photon, and you get lasing. So it applies really across a huge spectrum, but I was really intrigued to find out that I'd never heard anyone give it a specific name.
So would you consider a sphere then to be the perfect shape?
Well, it depends again. So if you want minimum energy, it's the perfect shape. If you want aesthetics, it may not be the perfect shape because it's a little boring, right? Aesthetics gets more interesting when you have something asymmetric in it usually.
If you take an egg, which is an oval, and you press it from end to end, you will not be able to break it.
Okay, so it may be that the chicken has figured out that that's the strongest shape for the egg. I guess that's what you're saying, right? The oval shape really has a lot of longitudinal strength.
Yes, it does.
Yeah, and it may be better than the sphere in that way. So that I guess that means that in some sense, the chicken's reproductive system is willing to put in extra energy to make a shape that isn't a sphere, but it has other benefits.
So it's a matter of application.
Yeah. Yeah, it depends on the application, yeah. And you don't necessarily want the girders in a bridge to be sphere-shaped. You want a different set of properties than just as at minimum energy.
Can foam help us with building structures?
I hadn't thought about that. Of course, it does in insulation. That's a huge deal. Oh, yes, I'll give you one good example. We can get back to aerogel. So aerogel was wonderful for this comet experiment because it had the property of stopping these speeding bullets, which I mean little pieces of comet moving at many miles a second. It could stop them without shattering them. That's why they used aerogel. But another great thing about aerogel is it's a wonderful heat insulator, and yet it can be made quite highly transparent, 80 or 90%. So you can imagine building a house with skylights that are made out of aerogel. They let in sunlight, 80 or 90% of what hits it, to warm your room, but because they don't conduct heat very well, the heat doesn't come out. It gets trapped in the room, which is just what you want if you wanted to do solar warming of the house. So yes, solid foam could help in construction, and as I said, we all know that it's good for wall insulation too.
Can metals be foamed?
Yes, that was one of the most fascinating things I found. At the time I wrote the book, there's only one company. Now I think there were several. They have techniques. They're trade secrets, so I don't know exactly how they do it, but they have techniques to take a whole bunch of standard metals. They can do it with aluminum and copper and also with carbon. And instead of having it come out as a solid ingot of the metal, it looks like a piece of Swiss cheese with many, many holes in it. They make foamed aluminum, foamed copper, and so on. And it's quite beautiful to look at. It has a very nice, interesting texture to it. And they use it for applications. We want the strength of the metal, but you don't want the metal to be good at conducting heat. Metals are good at conducting heat, but if you fill them with holes, they don't conduct as much heat.
Well, and it would make it lighter, too.
And lighter. So they've been used a lot in aerospace applications. That's correct.
Is it possible to make transparent aluminum like they did in Star Trek 4?
No, that's a tough one. The only way I could think to do it would be to put so many holes in it there would be hardly any aluminum left, and then it wouldn't have any strength at all. See, the thing about metals is the properties that make them metals, which is that they have many, many electrons, also make them opaque. So you'd have to pull in two different directions. Making a transparent metal is almost destroying the definition of what a metal is.
It would just be perforated.
Perforated would be the best you could do. But the little strands of metal, Each one of them would still have the properties of a metal. You just wouldn't have very much metal in this little ingot.
Are clouds a type of foam?
That's a good question. No, I don't think so. I think they're droplets of water. It's the same question as asking, is a fog a foam, and it isn't. If you drive through a fog, what you see is droplets of moisture appear on your windshield. So you're not seeing bubbles, you're seeing little chunks of water. And I think walking through a cloud is just like walking through a fog.
Why do bubbles pop?
Too much pressure. Pressure may build up and the skin may weaken. One thing you don't notice in daily life, but again, I have a photo in my book that shows this is, if you let a foam just stand, well, remember, all you're talking about is bubbles packed next to each other. The walls are made of liquid. Gravity is always pulling that liquid down. So after a while, the walls get thinner, and after even longer, they may get so thin that they can't withstand the pressure inside, and then the wall pops.
Yeah, why does bubble bath create more bubbles than soap?
I don't think I have a specific answer to that, but definitely there are compounds you can think of that make either faster walls of liquid or stronger walls of liquid, and that therefore give you a better foam when you mix them with water.
Sorry, it's the surface tension of the bubble.
Right. And surface tension is just another way of saying how strongly are the molecules in the surface of the liquid linked to each other. That's what surface tension is all about. It's how the molecules interact. So some smart chemist, however many years ago bubble bath was invented, figured out the right compound that would be harmless to people. They could probably make it smell good and look good, and also have the right surface tension to make really robust foam, really robust bubbles, and therefore robust foam.
Why do sparkling wines taste better when the bubbles are smaller?
That's a really interesting one. It has to do, it's kind of an indicator of how long the wine has been held in the bottle, or how well sealed the bottle was. Making champagne and other sparkling wines is a long process. It's a process where you put the wine in a bottle, you add some more sugar, and let it ferment inside the bottle. You cork it and let it ferment inside the bottle. That creates bubbles and the pressure builds up. If the cork leaks a little bit, or if the bottle's been held too long, some of that carbon dioxide will escape. And that means you have less pressure in there than you would like to have, and that results, it turns out, in bigger bubbles rather than smaller ones. So if you see bigger bubbles in a glass of what should be expensive champagne, that champagne has not been treated right. And that's an indicator that it's not in the best condition. That's my second, it's not a cooking tip, it's my second drinking tip for the day. I'll tell you a little tidbit, which is really cute. I checked this for my first book, and I rechecked it for my second book. But when Heineken brings out a batch of beer, they have an instrumentation that measures how long the foam lasts. Because studies have shown that beer drinkers think the foam is really an important part of the experience. They like to look at it, they like to drink through it, and as the liquid level goes down, they like to see that there's foam on the side of the glass. That's called cling. So Heineken is very aware of this, and when they make a new batch of beer, they have instruments that measure how long the head lasts. And if it lasts less than 30 seconds, that batch is gone. They reject it. And I do like Heineken, so I'm glad to know that they take that much care.
I wonder what they do with this rejected beer.
That's a good question. Maybe you and I ought to be there on rejection day.
Yeah, I'm going to go in for a rejection day special.
Because we would still find it acceptable, probably, right?
Right. We've discussed the macro, but how about the micro? Can foam be found in the microverse?
Yes, that was really great fun to write about. It's very hard to get your head around what it would look like, but I can say in words what we're talking about. So one of the huge problems in physics these days is exactly like what we've been talking about. How do you connect the macro world to the micro world? The macro world we have a handle on. We kind of know how galaxies work and planet orbits and so on, and all of that goes back to the theory of gravity, Einstein's theory of gravitation, which really works very well. As far as we know, it's 100% cool. It's good. Microworld is all about quantum mechanics, and we know how to do that. We know how to manipulate atoms, and we can make wonderful micro devices and nano devices and so on. We don't have a theory that explains both of them. So people are really scratching their heads, and this has been going on for decades. I say people, I mean theoretical physicists are really scratching their heads for decades. How do you bring the two together? Well, one way to bring them together is to maybe hope that you can explain gravitation in a quantum mechanical way. And to do that, you need to assume that the way, way down at the basic structure of the universe, what space-time is really made of, you have to assume that's quantum mechanical. So one image that has come up is that way, way down at that tiny, tiny scale that we can't even measure, space-time is made up of little quantum bubbles of reality. That's been called quantum foam. I don't know if he invented the name, but Stephen Hawking has used that phrase, and other people use it too. So that's where the idea of a foam comes all the way down to the roots of the universe. No one has ever seen quantum foam. No one even knows it really exists, but it's a very intriguing hypothesis about how to get the macro and the micro to talk to each other, to form one unified theory.
Would this conflict with superstring theory?
Superstring theory is an alternate way to explain quantum and gravity, so it's a second theory, and a lot of people like it, but it also does not have one little scrap of experimental evidence, and there's some reason to think that you actually could not verify it experimentally. So string theory is kind of controversial.
So if you cannot prove something experimentally, you can't call it fact?
Really well said. I would say that sums it up. You can have very beautiful theories, and you admire the minds that do the math and put together the concepts and so on, and you're certainly willing to consider it. But physics is an experimental science. You know, we do things in labs, we build giant accelerators and so on. If you can't do an experiment that confirms it, you don't have the answer yet.
Sometimes I think it's just very clever math.
Yes, there is some of that. I just wrote a piece about this topic, and I made the same comment. And I went on to say, the beautiful math's the beautiful math, but don't let it seduce you. You really have to go the next step. There's a famous quote from Einstein. I use it in this article I just alluded to. He said that something like, if you're out to look for truth, leave elegance to the tailor. In other words, a beautiful mathematical theory is beautiful, but it's not enough. The truth is more important.
Yet Brian Greene would call it the elegant universe.
And, you know, he wrote a great book about it, and I've met him. He's a nice guy. He's a good writer. He took on a very tough topic. The fact remains there's not one scrap of evidence that string theory is right. Not one scrap of experimental evidence.
What about the Weir-Phelan structure? There's not a scrap of evidence that that's real either.
That's another thing I was able to update in the book, the latest version of the book, because when I first wrote it, this wasn't known. Now.
Sorry, in all fairness to the audience, Sidney, let's explain what a Weir-Phelan structure is.
Let's explain it first. Yeah, okay. So I said earlier, and I'll just repeat it, if you have an individual bubble, it's a sphere. But if you start pressing bubbles together to make foam, you have to ask yourself, what kind of shape do they take? And that shape is much more complicated than the sphere. A very famous physicist, Lord Kelvin, worked on this problem in the 19th century. He came up with a very strange-looking structure. As I said, it looks like one die out of a pair of dice that has had too much beer because it has very strange angles. It has 14 sides, 14 faces. That was one guess at the structure. Turned out not to be quite right. Then much later, just a few years ago, an Irish physicist named Dennis Weir and a graduate student named, I'm sorry, I don't remember his first name, but his second name was Phelan, so it's Weir-Phelan, came up with a structure which is taken to be the best known solution for the shape of the bubbles inside a foam. That's called the Weir-Phelan structure. And they first worked it out mathematically and then did an experiment. Here we go again. Theory first and then experiment. Did an experiment. We were actually able to find it in a foam. It's not yet known that this is absolutely the most perfect structure because we don't yet know if it has the lowest energy. It's the best structure that anyone has found up to this date. And I have a picture of it in the book. It's quite a monstrous-looking thing, really complicated. And the other interesting thing was, once it became known that the weophilin structure had a lot to do with foam, when the Chinese put on the Beijing Olympics in 2008 for their swimming center, they called it the National Aquatic Center, they made the outside of it look like the weophilin structure. I have a picture of that in the book, too, and it's really very striking.
People like detergent that have a lot of bubbles in it, right? Are the bubbles actually cleaning the dishes?
Yes, I think that bubbling action does do some good. I believe that it's used in water purification. I may be wrong about this, but I think it is, because the action of the breaking bubbles provides some scouring action. So I think that's right. Now, the bubble can't just sit there. They need to be moving or breaking, but if they do that, you get a little more mechanical motion, and that's got to help in cleaning.
Why does the ocean produce a foam? Is it full of soap?
Yeah, that would be wonderful. We would never have to take the bath again, just go for a dip. Well, it's full of stuff. It's full of molecules that provide enough surface tension that when a bubble forms, it doesn't just pop right away, but stays for a while. So another way to think about it is pure water will never make a foam. It'll make a foam as long as you shake it. But the second you stop shaking, those bubbles go away because there's not enough surface tension to hold them. Water that is impure, and I don't mean the ocean is not a place you want to be in, it has stuff in it beside H2O. It has dissolved salts and lots of other things. Stuff like that can make strong surface tension. So seawater can produce strong walls and bubbles, and therefore it can make a foam. And one of the amazing things I learned when I wrote the book, I just want to quote this again because your listeners might find it interesting too. When you listen to the roar of a breaking wave, which sounds so strong and so powerful, it's really everyone's memory of the power of the ocean. What you're really hearing is millions, billions, and trillions of bubbles breaking as the wave rolls over from its top. That's the sound of breaking foam on a massive scale.
That's a good factoid.
Isn't that a nice factoid? Yeah.
How can foam influence the weather? I asked you earlier if clouds were foam, but they're not. But do they have any other implications on the weather?
Another way it can, and it ties right into what we just talked about. So the ocean can form foam, and that's not only on a beach. It's out on the open sea. If there's enough wind, you get whitecaps. You get patches of foam. Well, as sunlight beats down on the ocean, where the ocean is its regular color, blue-green, it absorbs the sunlight. But where there are whitecaps, it reflects the sunlight. So the total amount of heat that the ocean deals with either absorbs or tries to send back out into space, depends on the amount of foam. And that is part of what sets the daily climate, the daily weather, but even more importantly, global climate. So the amount of foam on the ocean has some effect on the global climate. It could conceivably have an effect on climate change or global warming.
Well, I can honestly say this is a fascinating book, and we've really only touched on many of the topics that are inside. Where can the audience find Universal Foam 2.0?
This is on Amazon. It's a regular Amazon Kindle book. If people just go on Amazon, and the simplest thing is just to type in my last name, Perkowitz. It'll bring up all of my books, and I think the first one on the list will be the most recent one, which is Universal Foam 2.0. I'd like to give a shout-out to the artist who did the cover. I think it's a very striking cover. She's a woman in the UK who read the original book, liked it, and did a nice drawing just because she liked the book. I got a hold of her when I put out this revised edition. She redid her drawing, made a beautiful cover out of it, and that's what you'll see if you look it up. Her name is Karen D. Tregaskin. I'll say that again, Tregaskin. She did a great job, and I'm really happy to mention her work.
Yeah, and this book has had many covers, about 6 or 7 different covers over the years, right?
Yes, because it had so many different editions. It had editions in a lot of different languages. My favorite one was the Italian edition, where instead of calling it Universal Foam, they called it La Teoria del Cappuccino, which means the theory of cappuccino. And I thought that was the best name in the world.
SidneyPerkowitz.net, that's the website, correct?
Correct.
So if you're the audience, check out SidneyPerkowitz.net, purchase Universal Foam 2.0, and follow Sidney Perkowitz's research. It's great stuff. Sidney, once again, thank you so much for being a guest on the program.
My pleasure. It's the third time. It gets better every time.